Students, in today's class, let us study about the material, its property when current is flowing through it. The first term that we are going to use and we are going to discuss that first is resistance. Let us write the symbol of resistance here in a bracket, and let me tell you the symbol of resistance that we are using is capital R. Fine. Let me show you people that current is flown through the wire. When current is flowing through the wire, it causes hindrance. We call this hindrance as resistance. So resistance is nothing but it is hindrance caused by the material for the flow of current. Let me repeat, resistance is hindrance. You know, hindrance is nothing but obstruction that is caused by the material for the flow of current. Fine. Let me take now the long wire. So let me show you people that the length of this wire is more, length of this wire is less. And let me tell you people that when the length of the wire is more, resistance here to the flow of current is more. Fine. You see here, resistance was less. When the length of the material was less, resistance becomes more when a length of the material becomes more. You can see the relation, length less, resistance less, length more, resistance more. So less, more. So you can say that length of the material and resistance in the material, they are directly related to each other. So we can write here, resistance is directly proportional to the length of the material. Let me take it as expression 1. Now what I am going to do is, I am going to take the material whose area of cross section is too large. You look at this, when the area of cross section was small, there was more hindrance to the flow. When area of cross section of the material is large, to the flow of current, the resistance or hindrance, it will be less. Please observe this. When area is less, resistance is more. When an area is more, you can see resistance is less. Let me repeat this particular fact. Area less, resistance more. Area more, resistance less. Let me use the term less, more, less. You can see they are inversely proportional to each other. So let me write, resistance in the material is inversely proportional to area of cross section. So let me take this expression as expression 2. Now on combination, you can see resistance I can see on a left side, you can see on the right side. In the numerator you have length, it is L, and in the denominator you people can see A. Fine. So on combination means not adding, it is just a combination. You can see left side we have R, you can see at the right side numerator L, denominator is area. Now what I am doing is, I am changing proportionality sign into equal, and we people know that whenever we are doing that, we need to introduce proportionality constant, and the proportionality constant we are writing is rho. So into L by E. So this is the expression of resistance. Let me put it in the box. And everybody knows that the unit of resistance is ohm. So everyone mentioned that unit of resistance is ohm. And the symbol of ohm is here. Fine. Now here, what is rho? Rho is nothing but resistivity, which is even called specific resistance. Let me write over here itself, where rho is nothing but resistivity that is even called specific resistance. Fine. Let us now find out the unit of resistivity or a specific resistance. So let me rearrange expression for writing the expression of the rho. Now what I am doing is I am writing rho one side. You can see another side we have R. When this particular term is going another side, A will go to the numerator and L will comes to the denominator. So A in the numerator and L in the denominator. So this is expression for rho. It is just the rearrangement expression of this. Fine. It is the rearrangement expression of this. Now I want to know what is the unit of rho, which is called resistivity or a specific resistance. So everybody see this. Resistance is ohm, area, length into breadth, meter into meter is meter square, and length here is meter. You people can see that 1 meter and 1 meter will get cancelled. What is left out is ohm, and in the numerator meter. So ohm meter is the unit of resistivity, which is even called a specific resistance. Let me tell you people that the unit of resistance is ohm and unit of resistivity is ohm meter. Now you see this, I want to define resistivity of the material, and I am defining resistivity of material in a physics style. So how you are defining things in physics, whenever you want to define something, you are equalizing that something with one more thing. Remaining, you are taking unity. Fine. See this. You want to equalize resistivity. You want to define it. You are equalizing this with resistance R. In order to equalize these, I should take area 1 square meter and length of the material is 1 meter. Now let us define resistivity as resistance in the material of length 1 meter and area 1 square meter. Fine. Let me repeat it. Resistivity is resistance in the material of length 1 meter and area 1 square meter. It is definition of resistivity of material. Fine. Yes. So it is all about resistance and resistivity. Now let me go for reciprocal of resistance and resistivity. So let me clear this. You all people know that the unit of resistance is ohm, resistivity is ohm meter. Now I want to study about a reciprocal of resistance. As you all know that the reciprocal of resistance is called conductance. So you write the next side heading conductance. And in chemistry, the symbol of conductance we always take is capital G. It is reciprocal of resistance. So everyone, conductance is reciprocal of resistance. Now everybody knows that resistance and length of the material directly proportional, resistance and area of material inversely proportional. We want to change proportionality sign into equal. While doing that, we need to introduce proportionality constant, that is rho. Now we all want to find out the expression of the G, that is the reciprocal of R. You can see the expression of R now. You are going to do its reciprocal. So I am writing now the reciprocal of resistivity. Reciprocal of L by A become A by L. Correct? Now conductance is equal to, what is reciprocal of resistivity? Reciprocal of resistivity is conductivity. And this is the unit of the symbol of conductivity, the reciprocal of resistivity, and I am writing A by L as it is. And this is a new expression, and let me put it in a box where you are writing the symbol K is conductivity symbol, and we call this particular symbol as kappa. Let me tell you people that it is kappa K. It is kappa K. Conductivity is kappa K. Fine. So this is called conductivity. You people know that. Resistivity called specific resistance. Even conductivity called specific conductance. In a similar way. In the similar way. Fine. So let me go for definition now. I want to define conductivity. So once again, the physics way of defining things. When you want to define conductivity, you equalize it with the conductance. In order to do their equalization, I need to take all these parameters unity. I need to take area 1 square meter. I need to take the length 1 meter. So we are defining conductivity as conductance in the material of length 1 meter and area 1 square meter. We are defining conductivity as conductance in the material of length 1 meter and area 1 square meter. Fine. Now see the unit of conductance and specific conductance. Now listen here. I am writing the unit of resistance. Everyone know it is ohm, and this is the symbol. Now I want to know the unit of conductance. Obviously it should be the reciprocal of ohm. You can write it as per ohm. The symbol you can write it as per ohm like this. It is 1 by ohm, that is per ohm. And please you read it as reciprocal of ohm. You reversely read it, it will become mho. So even you call the unit of conductance as mho. You are just reading it reverse. MHO, it is nothing but mho. But popularly it is called as Simon. Let me tell this to you people that resistance is ohm. Conductance is reciprocal of ohm, that is called a per ohm. It is a symbol. When it is per ohm, you reversely read it, it will become mho, which is popularly called a Simon. So let me use per ohm in the place of that, the term, the symbol of Simon. Fine? Yeah. Let me go ahead. And let me tell you people that when we talk about resistivity, the unit we said ohm meter. Now I want to know about the unit of conductivity or a specific conductance. I know it is reciprocal. The reciprocal of ohm is a Simon. Just now I said it. Reciprocal of meter is per meter. Simply I can write it as Simon per meter. So let me just in brief let me tell you people that the units of resistance ohm, resistivity ohm meter, conductance Simon, and the conductivity is Simon per meter. So this is all about the brief introduction of resistance, conductance, resistivity and conductivity. Let me clear this out. Okay. We shall study now about its continuation part. Fine. Let me speak now about conductions of two types. What you do is you study this through columns, differentiating two types of conduction. In a one column, you people write metallic conduction. In another column you just write electrolytic conduction. In a one column we have metallic conduction, in another column we have electrolytic conduction. Okay, now how you are studying this metallic conduction? What you do is you show a metal sheet, You show a metal sheet, and you know that a metal sheet is made up of metal atoms. Metal sheet is made up of metal atoms. Let me show you metal atoms with the valence electrons of the atom. Fine. Now let me tell you people that I'm talking about alkali metal, alkaline earth metal, which is present at initial spot of periodic table. You know that when you move across the period, atomic size it go on decreases. That says that atomic size of metal atoms always larger, because I know that metals are present in group 1 and group 2, so that in the beginning atomic size will be huge. When I will say that, let me show it here. When I will say that metal atom having its atomic size larger, the distance between the nucleus and valence electron is too large. When a distance is too large, attraction is too weak. When an attraction is too weak, you are saying that electron is freely moving. So in the metal atom, we are saying that valence electron is loosely held by the nucleus, so that they are become freely moving particles. So here in the metal atom, in the metal sheet, we have electrons present which are freely moving. Now what let me do is, let me connect electrodes here. Let me connect electrodes there. Let me apply electric field. When I will apply electric field, electron will be injected in. Fine. Now what exactly this electron will do after it enters the metal sheet? This electron which entered will push this electron here, and this electron which is present here, it will be ejected out. You can see when you apply the electric field, as electron comes in, at the same time, same quantity electrons that will be ejected out. Fine. If 10 electron comes in, 10 electron goes out. If 20 electrons comes in and 20 electron goes out. So you can see that metallic conduction is nothing but the flow of electrons. So we call metallic conduction even as electronic conduction. So we call metallic conduction also as electronic conduction. So let me write this in the bracket in the heading itself. So I'm writing the first point. It is due to the flow of electrons. The flow of electrons. Therefore we call it as electronic conduction. Let me go to the next column where we have electrolytic conduction. So let me show you the electrolytic cell. The electrolytic cell comprising of electrodes. Electrodes are dipped in electrolyte. For example, let me say AB, electrolyte. Now what I'm doing is I'm connecting these electrodes to the battery. You know that it is a positive terminal of the battery. This is negative terminal of the battery. When you apply electric field, exactly what happened, A plus move towards the negative electrode and B minus will move towards the positive electrode. Can you see electrolytic conduction is due to the movement of ions? Therefore we call electrolytic conduction also as ionic conduction. So please mention that in the bracket here itself in the heading. It is nothing but ionic conduction. So write the first point. It is due to the flow of ions. Fine. Let me discuss now the second point here. So look at here, pay attention, see this. Now you know that during metallic conduction, if 10 electron came in, 10 electrons went out, n electrons came in, n electrons went out. That means chemical change in the metallic conduction is not happening. Correct? You're saying that 5 electrons coming in, 5 electrons going out. That means there is a no chemical change occurs during the metallic conduction. So that is what we are taking as a second point. So please write it. There is no chemical change occurs, no chemical change occurs during metallic conduction. Simple. Let me come here. Please see this. During ionic conduction, during electrolytic conduction, A plus went on negative electrode, negative positive, it will become neutral. You can see during ionic conduction, B minus went on a positive electrode on an electrode, plus minus become neutral. Can you see A plus become A and B minus become B? Chemical change happening during the electrolytic conduction. So that is what we are writing as a second point. We are saying that chemical change occurs during electrolytic conduction, which is even termed as ionic conduction. Let me go for a last point, third point. Let me speak here about temperature. See this, I am talking about temperature. You all people know that there are particles. If present in the system, you increase the temperature, particles oscillation becomes more. Particles vibration becomes more as you increase temperature more and more. Exactly what happened, you see. Electrons are flowing across the metal sheet. You know that positive ions are also present. Now exactly what happened, as you increase the temperature, these ions, their vibration becomes more, their oscillation becomes more. You can see electron flowing, it is having now more and more obstacles, it is having more and more obstruction. So you are saying that electronic conduction becomes less as you increase the temperature. So what I said is, as you increase the temperature, these ions, their oscillation becomes more, so that electron flow becomes less, electronic conduction becomes less. So we are saying that metallic conduction becomes less as you increase temperature. So let me write here, as temperature increases, metallic conduction decreases. So the last point I am writing that side under electrolytic conduction column. You all people know that as you increase temperature, the mobility of ions becomes more. Mobility of ions becomes more, ionic conduction becomes more, electrolytic conduction becomes more as you increase temperature. So let us write, temperature increases, electrolytic conduction, which is even called ionic conduction, increases. So this is all about the differences between the electrolytic and metallic conduction. The side heading, factors affecting metallic conduction. The first factor, please see this, I'm talking about the material. You assume that material having area of cross section less, you know that resistance to the flow here is more. Now if you consider material where area of cross section is more, that means here resistance to the flow is less. That means conduction in the material, it depends upon the shape of the material. So the first factor that is affecting metallic conduction is shape of the metal, or you can say geometry of the metal. The second factor, let me take up the second factor. Now you assume there is a metal sheet containing metal atoms containing one valence electron at each metal atom. Let me consider another metal sheet which is made up of metal atoms, and let me assume that each metal atom has the two valence electrons. Now you can just make out where metallic conduction is more. It is obviously in the second sheet, because we know that number of electrons in the valence shell per atom is more, electronic conduction is more, metallic conduction is more. Number of valence electrons per atom is less, electronic conduction is less, metallic conduction is less. So we are saying that the metallic conduction, it even depends upon the number of valence electrons per atom. So what I said is, number of valence electrons per atom is more, electronic conduction more, metallic conduction more. Number of valence electrons per atom is less, electronic conduction less, metallic conduction is less. So the second factor we people are writing here, it also depends upon the number of valence electrons per atom. Third factor already we discussed, that is temperature. What I said is, when temperature you increase, oscillation of positive ions becomes more. When oscillation of positive ions becomes more, obstruction to the flow of electron becomes more. When electron flow becomes less, electronic conduction becomes less, that is metallic conduction becomes less. If you want, you just add up the point which has already been discussed by us, and already you just took it as a point in the notes, but still if you want, you just write it in a one line. As temperature increases, metallic conduction decreases.